Hi, this is the Trigonometry Lectures for Educator.com, and today we're going to learn about probably the single most important identity in all of trigonometry, which is the Pythagorean identity. It says that sine squared of x plus cosine squared of x is equal to 1. So this is known as the Pythagorean identity. It takes its name from the Pythagorean theorem, which you've probably already heard of. It says that the Pythagorean theorem says that if you have a right triangle, very important that one of the angles be a right angle, then the side lengths satisfy a squared plus b squared equals c squared. So you've probably heard that already. The new fact for trigonometry class is that sine squared of x plus cosine squared of x is equal to 1. And what we're going to learn as we work through the exercises for these lectures is that these are really two different sides of the same coin. You should think of these as being sort of facts that come out of each other. In fact, we're going to use each one of these facts to prove the other one. So these are really equivalent to each other. So let's go ahead and start doing that. In our first example, we're going to start with the Pythagorean theorem. Remember, that's a squared plus b squared equals c squared. And we're going to try to prove the Pythagorean identity, sine squared x plus cosine squared x is equal to 1. So the way we'll do that is let x be an angle, and let's draw x on the unit circle. The reason I'm drawing it on the unit circle is because, remember, the definition of sine and cosine is the x and y coordinates of that angle. So if we draw x on the unit circle, the hypotenuse has length 1, and the x coordinate of that point, remember, is the cosine of x, and the y-coordinate is the sine of x. Now what we have here is a right triangle, and we're allowed to use the Pythagorean theorem. We're given that, and we're going to use that and try to prove the Pythagorean identity. So the Pythagorean theorem says that in our right triangle, by the Pythagorean theorem, let me draw my right triangle a little bigger. There's x, there's 1. This is cosine x. This is sine of x. By the Pythagorean theorem, one side squared, let me write that first of all as cosine x squared, plus the other side squared is equal to 1 squared. That's the length of the hypotenuse. But then if we just do a little semantic cleaning up here, 1 squared, of course, is just 1. Cosine x squared, the common notation for that is cosine squared x plus sine squared x is equal to 1. So we've just derived an equation, and look, this is the Pythagorean identity. So what we've done is we started by assuming the Pythagorean theorem, and then we used the Pythagorean theorem to derive the Pythagorean identity. Let's see an application of that in the next example. We're given that theta is an angle whose cosine is 0.47, and theta is in the fourth quadrant. We have to find sine theta. So let me draw theta. Theta is somewhere down there in the fourth quadrant. I don't know exactly where it is, but theta looks like that. And here's what I know. By the Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. So I'm going to fill in the one that I know, cosine theta. Cosine theta is 0.47, so this is 0.47 squared is equal to 1 plus sine squared theta. Now 0.47, that's not something I can easily find the square of, so I'll do that on my calculator. 0.47 squared is 0.2209, so that's plus 0.2209. Sine squared theta is plus 0.2209 is equal to 1. So sine squared theta is equal to 1 minus 0.2209, which is 0.7791. So sine theta, if we take the square root of both sides, sine theta is equal to plus or minus the square root of 0.7791, which is approximately equal to 0.8827. Now it's plus or minus because I know that sine squared is this positive number, but I don't know whether the sine is the positive or negative. But we're being given more information in the problem. Theta is in the fourth quadrant. And remember, sine is the y coordinate. So the sine in the fourth quadrant is going to be negative because the y coordinate is negative. So because theta is in quadrant 4, sine theta is going to be negative. So we take the negative value. Sine theta is approximately equal to negative 0.8827. So the whole key to doing this problem was to start with the Pythagorean identity. Sine squared theta plus cosine squared theta is equal to 1. Once you're given sine or cosine, you can plug those in and figure out the other one, except that you can't figure out whether they're positive or negative. The identity doesn't tell you that, so we had to get this little extra information about theta being in the fourth quadrant. That told us that the sine theta is negative, and so we were able to figure out that it was negative 0.8827. Let's try another example of that. We're going to verify a trigonometric identity. Now this is a very common problem in trigonometry classes, is you'll be given some kind of identity involving the trigonometric functions, and you have to verify it. For this one, what I want to do is start with the right-hand side. So I'm going to label this RHS. RHS stands for the right-hand side. So the right-hand side here is equal to sine theta over 1 minus cosine theta. Now I'm going to do a little trick here, which is very common when you have something plus something in the denominator or something minus something in the denominator. And the trick is to multiply by the conjugate of that thing. So here I have cosine theta or 1 minus cosine theta in the denominator. I'm going to multiply by 1 plus cosine theta. And then, of course, I have to multiply the numerator by the same thing, 1 plus cosine theta. Now, the reason you do that, this is really an algebraic trick, so you probably have learned about this in the algebra lectures, but the reason you do that is you want to take advantage of this formula, a plus b times a minus b is equal to a squared minus b squared. So that's often a way of simplifying things using that algebraic formula. So what we get here in the numerator is sine theta times 1 plus cosine theta. In the denominator, using this a squared minus b squared formula, we get 1 minus cosine squared theta. Now let's remember the Pythagorean identity. The Pythagorean identity says sine squared theta plus cosine squared theta is equal to 1. That means 1 minus cosine squared theta is sine squared theta. So we can substitute that into our work here. Sine theta over 1 plus cosine theta times 1 plus cosine theta. Now the denominator, by the Pythagorean identity, turns into sine squared theta. And so we get some cancellation going on. This sign in the numerator cancels with one of the signs in the denominator, leaving us just with 1 plus cosine theta over sine theta in the denominator. And look, that's the same as the left-hand side that we started with. So we started with the right-hand side, and we were able to work it all the way down and end up with the left-hand side, verifying the trigonometric identity. The key to that one, there were sort of two key steps there. One was in looking at the denominator and recognizing that it was a good candidate to invoke this algebraic trick where you multiply by the conjugate. If you have a plus b, you multiply by a minus b. If you have a minus b, you multiply by a plus b. Either way, you get to invoke this identity. So here we had a minus b, we multiplied by a plus b, and then we got to invoke the identity and get something nice on the bottom. The second trick there was to remember the Pythagorean identity and notice that 1 minus cosine squared theta converts into sine squared theta. Once we did that, it was pretty easy to simplify it down to the left-hand side of the original identity. So we'll try some more examples later.